What Nusselt number correlations are best for convection? Imagine trying to figure out how heat moves from one object to another without touching them. That's what convection is all about, and understanding it helps us design better cooling systems and heat exchangers. But how do we predict how effective convection will be? That's where Nusselt number correlations come into play. They are formulas that help us estimate the heat transfer rate in different situations. The best correlations depend on the type of convection. For natural convection, where fluid moves because of buoyancy caused by temperature differences, the Nusselt number is usually related to the Rayleigh number. The Rayleigh number combines the effects of buoyancy, fluid properties, and temperature difference. For vertical plates, the Churchill-Chu correlation is often used because it accounts for both laminar and turbulent flow regimes. For horizontal plates, the McAdams correlation is common. These formulas generally express the Nusselt number as a function of the Rayleigh number and the Prandtl number, which compares how fast momentum diffuses to heat diffuses in the fluid. In forced convection, where external forces like fans or pumps move the fluid, the Nusselt number depends mainly on the Reynolds number, which measures the ratio of inertial forces to viscous forces, and the Prandtl number. For turbulent flow inside pipes, the Dittus-Boelter correlation is popular. It states that the Nusselt number is proportional to Ra raised to the power of 0.8 and Pr raised to a certain power, depending on whether the fluid is being heated or cooled. For transitional and turbulent pipe flows, the Gnielinski correlation offers more accuracy across a wider range of flow conditions. External flows over cylinders or objects often use correlations like the Joukowska's or Hilpert formulas, which take into account the shape and flow speed. When flows involve both natural and forced convection, called mixed convection, engineers often combine the Nusselt numbers from the natural and forced formulas. They consider whether the flows help or oppose each other to get the right estimate. Picking the best correlation depends on the flow regime, whether it is laminar, transitional, or turbulent, as well as the shape of the object and whether the flow is inside or outside. In real-world applications, these correlations are used to design heat exchangers, cooling systems, and to predict how heat moves around objects. Using the correct correlation ensures accurate calculations, which helps make systems more efficient and reliable. Remember, there is no single perfect correlation for all situations. Instead, choosing the right one depends on understanding the flow type, geometry, and fluid properties. That way, you can make the principles of heat transfer work for you in practical ways.